Hi, this is Somaiah, working as assistant professor in the Department of Mechanical Engineering. Welcome to the closed conduit flow. Today, as I have planned to introduce the closed conduit flow. Previously, I have discussed the various fluid static properties and fluid dynamics, etc. So then today we are going to discuss the flow through closed conduit flow and introduction to Reynold experiment. A pipe is a closed conduit which is used for carrying fluids under pressure. Pipes are commonly circular in section. So as the pipes carry fluids under pressure, the pipes always run full. So the pipe cross section may be so based on the requirement and economical cross section of fluid pipes will be considered as a circular. It may be a rectangular or trapezoidal section and square section. Any pipe cross section will be considered, but the majority of due to from economical point of view, from fabrication point of view, pipes are will be in general it may be circular. The fluid flowing in a pipe is always subjected to a resistance due to shear forces between fluid particles and the boundary surface. So when the resistance of flow of fluid in general known as the frictional resistance. So due to this frictional resistance, the pressure drop will be taking place. Since a certain amount of energy possessed by the flowing fluid will be consumed in overcoming this resistance to the flow, there will always be some loss of energy in the direction of flow, which however depends on the type of flow. So it may be laminar or turbulent flow. So there will be, based on the type of flow, there will be a drop. So the fluid flow in a pipe may be either laminar or turbulent. So whenever the fluid is entering into a pipe opening, so if there is a the pipe cross section, if you take as a circular at the entrance, so at the entrance what will be there? So if you draw a fluid particle flowing through a pipe, so consider a length of a pipe is L. Then if you draw a pressure drop, pressure graph for this particular pipe. So initially the pressure will be at the entrance it will be high. So if you assume that this is the pressure, so at the entrance of your pipe, but at the entrance of your pipe there will be a loss, a pressure loss will be there at the entrance. So therefore the actual curve will be begins from here. So this is nothing but this gap is known as the entry loss of a pressure, entry loss of a pressure. So this much of entry loss will be there. So at the distance 0, this is the loss, because at the entrance loss of head due to entrance, at the entrance pressure loss will be taken place, that will be equal to this much of magnitude. Then if you consider at x equal to L by 2 and x equals to L, so from L by 2 to L, this is a constant. Dou P by dou x, this is a pressure gradient. Dou P by dou x is a constant. So here this is nothing but this gap is known as a fully developed flow. Fully developed flow. This region is also known as fully developed flow. So and this is here entry flow. This is known as entry flow region, and here there will be a loss due to entrance. So after that the fully developed flow will be existing, and you can take dou P by dou x is constant. Constantly it will go on decreasing, because over here a length of pipe, as long as the length of pipe is going to increase, then due to frictional resistance the total energy also will be lost. So that is known as loss of head due to friction will be existing. So therefore, so this difference is pressure gradient, pressure difference. This much of pressure difference, delta P, will be taking place. So if you consider only fully developed flow, so otherwise this is a loss from from exit point of a pipe to the initial entry point of a pipe or initial point of a pipe is we can take as delta P. This is the pressure drop will be going to exist. So at the entry, this there will be entry loss denoted by HI. After that, it will be added with the loss of head due to friction. So loss of head due to friction will be greater than to any other force, any other loss. So therefore this will be considered majorly. So but any pipe if you consider that will be with some resistance, it will offer some resistance because no pipe is ideal pipe. Always irregularity will be existing there. Therefore so while we are using real fluid and real pipe, in case so only ideal fluid will have zero viscosity. Therefore and there will be losses will be negligible. So but in this real fluids, when you use real fluids and real material, always it offer resistance. Therefore these are unavoidable in a real life. So the importance of a pipe is generally we'll be observing in household water supplying applications and in gas supply also, and then sewage flows, the transportation of chemicals, then petroleum, chemical industries. In lot of industries, the pipe will be the flow is required either a chemical or any liquid, not only chemical, any liquid or any gas. If it is to be transported from one point to another point, definitely there is a requirement of pipe. So either in case of liquids, liquids you can use open channel flow. In case of water, you can apply open channel flow. Some portion is open to the atmosphere, or some portion of pipe is open. So but in case of if you transport to a full extent to maximum efficiency, then it has to run full. So then only there will be a economically we can transport liquids from one point to another point. In some chemicals, it should not be exposed to the atmosphere. So therefore, where open channel flow is not recommended in case of chemicals and petroleum, it must be closed. It should not be open to the atmosphere. Therefore, only the closed conduit flow is applied. The closed conduit, therefore, we are going to discuss closed conduit flow. Closed conduit flow, so there are some limitations if you use, if you transport chemicals and petroleum, some liquids and some gases. So if it is open to the atmosphere, there will be some problems and some danger will be taken place. So in order to avoid some harmful effects to the atmosphere, we have to apply, we have to go through closed conduit flow. The existence of two types of flow, laminar and turbulent, was firstly demonstrated by Osborne Reynolds in 1883 with the help of a simple experiment. So the Reynold experiment, from then onwards it was called as the Reynold experiment. The Reynold experiment, the main objective is to visualize the laminar flow and the transition zone as well as the turbulent zone. How the liquid is going to transform, the fluid flow is going to take place from laminar into transition, then from transition into turbulent. That was firstly demonstrated by Reynold. So this is a very simple experiment. Here we can see. So in this experiment, we can observe there is a tank filled with a water, and there is a small a container will be there. So with it is in order to hold a different liquid with a different color, whose specific weight will be equal to the specific weight of water, so that it can flow along with the water. Otherwise, there will be a problem. So we can't visualize the difference between the water and the liquid dye. So if the liquid dye is taken in a container, and if you open the delivery valve, so this is a glass tube, a transparent glass tube, so that we can see how the fluid is flowing and what are the so in what way it is in which pattern it is moving, and how liquid dye is moving through the liquid or through the water, or through at what point it is moving, and in what fashion it is moving. We can observe all these things once it is a glass tube. So at the end of a glass tube, it is connected to a delivery valve. So if the delivery valve is open fully, so they were to its maximum capacity, to its highest velocity, it can be moving. The water will flow to its maximum velocity whenever it is open fully. So to its maximum velocity it can be, but we assume that initially it is fully closed. Initially it is fully closed. Okay, there is no flow of water, there is no flow of liquid dye through a bell-mouthed entrance of a glass tube. It's known as bell-mouthed entrance of a glass tube. So at this entrance we are going to inject a liquid dye with a different color whose specific weight is equal to the specific weight of water. So then only it can flow along with the water. So in this case, we assume that gradually the delivery valve is open. So open to the 1/4, at 25% it is open. In this case, you assume that so gradually water is flowing. In that case, the liquid layers are very straight line. You can observe the while the water is flowing. Initially, you don't need to open the dye. So the dye is not opened. Only the liquid is flowing. So at its lowest opening. So in that case, you can see the water is flowing without any disturbance, and the water fluid layers will be moving one over another without disturbing between each other. So in that case, I am going to apply at this point. I am going to open the liquid dye. Then the liquid dye also starts moving along with the flow of liquid. So in this case, so what you can see, what you can observe is initially when the velocity is low to a small opening, so there is a straight line of a liquid dye. You see the orange color liquid dye. This is a very straight line. You can see that means a laminar flow. In the laminar flow only, in the case of laminar flow only, the liquid particles will move without disturbing other fluid particles or other fluid layers. Then only you can visualize the fluid particles, the fluid of a different color fluid with a straight line. So whenever the valve is open further, or 50, if it is open to 50%. So if it is open to its 50%, then gradually the velocity of the liquid will be increasing. As the velocity increases, the fluid particles or fluid layers may not be stable. So gradually they will be converging from laminar to they become they are going to disturb, and they are going to transform into other zone. So therefore it becomes a wavy one. So the wavy one indicates they are about to transform from one pattern to other pattern, and this is nothing but this is a region of a transition where where so one pattern a laminar is going to is no more stable, no more laminar. It is going to transform into another one. So therefore we can call it as a transition zone. So if you open further, so 3/4, or if you open 100% of gate opening, exit valve is opened fully. So in that case, what happens? So the wavy one also may not be stable. It will be diffused. It becomes a diffused one. So in this case, we can see whenever based on the exit velocity of a delivery valve, the liquid velocity, water velocity also will be increasing. Due to that, the fluid particles or fluid layers may not be stable, and they are going to be transformed from laminar into turbulent. Up to this, you can call it as a laminar. If you increase, then it becomes a wavy one. This indicates a transition zone. If you open furtherly, the transformed, the wavy shape one becomes a diffused. So the diffused one, the fluid, whichever we are transmitted through a separate container with a different color, the dye becomes diffused, whose fluid particles becomes diffused. So here the liquid dye is straight. Afterwards it is wavy one. It is become wavy one where it is a transition zone, it is a laminar zone. So if you open furtherly, so then it becomes the wavy one becomes diffused, it becomes scattered. Therefore you can recognize that this beginning of a turbulent, where the turbulent zone begins. So based on the exit velocity, so this is a simple demonstration with the help of a glass tube which is connected to a liquid container. So where through which we another liquid with a different color we have taken, whose specific weight is equal to the liquid which we are having in a container, and so that we can visualize these two different colors. So how the fluid is flowing based on the velocity, how it is going to vary. So whenever it is laminar, the Reynolds number will be less than 2000. If the laminar Reynolds number is in between 2001 to and 4000, then you can call it as a transition zone. And if the greater than 4000, then we can call it as a turbulent flow. So this was demonstrated by a Reynold with this experiment. So based on the velocity of flow, the dye will remain constant. It may be stable, it may be unstable. So based on that, it was described as we had discussed in previous slide. So here we can see very clearly in case of laminar, the liquid dye is they are very straight without any disturbance. It's a perfectly horizontal line, and it is parallel with the remaining fluid particles how they are moving. So they are also laminar, and so this is also moving along with that. Therefore, this is also laminar. We can recognize how other fluids also there. So and in case of transition, it becomes a wavy one because it won't be stable. Gradually, it transforms from laminar into turbulent. In this case, we can observe the scattered, the diffused dye. So therefore, we can say this is nothing but a turbulent flow. If you see this type of pattern, we can call it as a turbulent, and this is nothing but a transition region, transition, and this is laminar. So from this case, we can say what is a laminar flow, and why we can understand what is a turbulent flow. So based on the liquid dye while it is moving with respect to the velocity. The velocity at which the flow changes from laminar to turbulent in case of a given fluid at a given temperature and in a given pipe is known as critical velocity. The critical velocity is simply whenever the fluid is changing from one phase to another phase. So that is nothing but critical velocity. The velocity at which it converts from laminar into turbulent, or laminar into transition, or transition into turbulent. That is nothing but a critical velocity. So the state of flow in between two types of flow is known as a transitional state or transition flow. So on the basis of experiments, Reynolds discovered that the concurrence of a laminar and turbulent flow was governed by the relative magnitudes of the inertia and the viscous forces. So here inertia forces, whenever inertia forces are predominant over viscous forces, so how it will be there. So if the viscous force is predominating the inertia force, so how it will look like. So in case of laminar flow, viscous forces are predominant because this will dominate inertia forces. In that cases, you can feel this type of pattern. So that is laminar flow. Here viscous forces are predominant. So here viscous forces gradually the inertia forces tries to dominate in this region. Here inertia forces will be dominant. So therefore we can say this is a turbulent zone, and the velocity at which it is converting to turbulent is known as a critical velocity, and based on the various forces governing the fluid, so based on that the type of flow or flow pattern will be existing. So it was indicated that low velocity of flow, even for the fluids having a very small viscosity, the viscous forces become predominant, and therefore the flow is largely viscous in character. However, at higher velocities, inertia forces have predominance over the viscous forces. So then we can say such type of flow is turbulent flow, and the relationship between these two forces only, inertia forces and viscous forces, is known as Reynold number. Therefore, the Reynold number is simply a ratio of inertia forces by viscous forces. So whenever based on the word dominance of inertia forces and dominance of viscous forces, we can define the pattern of flow. Which type of flow is there? Dominance also based on the velocity of a fluid which is flowing through the pipe. So if the velocity is greater, then viscous forces becomes a predominant over a inertia forces becomes a predominant over a viscous forces. If the velocity is low, at lower velocities, the viscous forces will predominate the inertia forces. Therefore, the relationship between these two forces is nothing but Reynold number. So, based on that, we can arrive at a number. That number is Reynold number. Based on that, we can say, so which type of flow it is. So therefore, based on the Reynold number, we can derive an expression for Reynold number based on the inertia forces and the viscous forces. So inertia force can be defined as mass times acceleration, F equals to ma. So inertia force is F equals to ma. Fi is equals to mass times acceleration. So we can write the mass is nothing but density into volume. So from this, the density into volume nothing but mass and acceleration. So this includes rho L cube into L by T square. Otherwise, rho L square V square. This is the dimension of inertia forces. Inertia force. A viscous force is nothing but shear stress into area. Stress into shear stress into area. Where shear stress is mu into dou V by dou y, and area is L square. So from this we can write mu VL. So this is the dimension of viscous force, mu VL. So the rho L square V square by mu VL. So from this rho VL by mu, this is a expression for Reynold number. So rho VL by mu or rho VD by mu. So you can write rho VD by mu or rho VL by mu. So based on this, if you substitute density of liquid, velocity of liquid, and diameter of the pipe, viscosity of that fluid which is flowing through the pipe, then you can find out Reynold number. So based on that, it's a dimensionless, and based on that we can say which type of flow is going to exist. So applying this concept, rho VL by rho VD by mu, the flow of any fluid circular pipe, so one may predict the flow will be laminar if Reynolds number is less than 2000. If Reynolds number is less than 2000, we can call it as a laminar flow. Otherwise, if it is exceeding 4000, then we can call it as a turbulent flow. So only these between these two numbers, there will be a transition flow. So this is laminar flow and turbulent flow. If the Reynold number as per this equation here, rho VD by mu is less than 2000, that is laminar, and if it is in between 2000 and 4000, that is transition, and if it is greater than 4000, that is turbulent flow. And from this diagram, from this graph, we can identify the upper critical velocity and lower critical velocity. So this graph is plotted between HF by L head and loss of head due to friction over a length HF by L, and against the velocity of a fluid through a pipe. So in a laminar flow, up to this there is a laminar zone, and so the slope is there is a perfectly see the aspect is HF by L V. It's a perfectly so inclined at 45 degrees. So therefore, yeah, up to this point, we can say laminar because it's a very straight line. And after laminar, at some point A, the velocity of fluid, if you increase, if the velocity of fluid is going on increasing only in this direction, if you increase after point A, So at point A, it is gradually changing its path. It's no more straight line. The slope is not proportional. So now at point A, the curve will be taking in this way. So gradually, if you go on increasing at point B at after A, so if you increase furtherly at B, so it is taking diversion in this direction. So, but this is in the reverse direction. So at point A, it is taking gradually up to B, it is a straight line. So after at B, it is taking diversion. The curve is it's no more straight line, but it's taking path from C. So from C to and exit. So it after C, the velocity variation will be between 1.7 to 2. So where velocity variation will be v power n. So n will be varying in this way. So in this region, we can call it as this is a transition. Yet B, in between this region, it is going to change. So the point at which it is taking diversion is upper critical velocity. So the point B is known as upper critical velocity, and the point A is known as lower critical velocity. So because at B, it's no more straight line and it will taking a different path. And where after the C, if you increase further velocity and then index n will be varying in this direction. Therefore, this is completely the turbulent zone. This is a turbulent zone. And at the point A, so the laminar transition zone is from year to year. So at point A, still I am increasing the velocity, but at B, it is changing the diversion like this is going on. But if you reduce the velocity from maximum velocity, gradually I am decreasing in this. So now V is in the reverse direction. If you go on decreasing the velocity, so what happens? But it has to. But if it is ideal, in ideal case, it has to flow in this direction only via C. Via B, C, B, A. It should come through C, B, A, but it won't come through B, but it will come to A. C directly it reaches to A. In while you are decreasing the velocity, it will be flowing in this direction. So therefore, so from this diagram, from this graph, we can understand what is upper critical velocity and what is lower critical velocity. The upper critical velocity means after that point, the velocity will be abruptly changing, and whose phase is directly changing from laminar into turbulent. Therefore, that is upper critical velocity, and at lower critical velocity is known as the velocity at which the transition zone begins and where gradually changes, but it maintains some the slope. But after B, it won't be no more the following of the straight line. There is no relationship, the directly proportionality relationship between HF by L versus V. So this is based on the velocity, how the laminar flow and transition flow. Where in the transition, how the laminar is getting into turbulent, we can observe, and based on the velocity only, if you go on increasing the velocity, the laminar flow will not be stable, therefore it will be transforming into the turbulent. So with the velocity at which it is gradually changing into turbulent is lower velocity, and the point at which it may not be stable, and directly abruptly there will be changes and it will be taking in different path. The velocity is known as upper critical velocity. Behind the point B, increasing the velocity will be found. There exists certain transition region extending up to point C. So during which there is an abrupt increase in the rate at which the loss of head varies. So after the region of transition has passed, again the curve obtained in the form of straight lines with slopes ranging from 1.7 to 2. However, if the velocity is gradually reduced from a higher value, the line BC will not be retraced. It will not be retraced because from C it will come to A directly. instead of points maybe along a curve CA as indicated by arrows. The figure point B is known as upper critical velocity. The point and point A is known as lower critical velocity. Corresponding velocities are upper and lower critical velocities. It is seen that up to A, the drop in pressure head due to frictional resistance is directly proportional, HF by L. So loss of head due to friction, HF by L is directly proportional to the velocity. Behind point C, the drop in pressure head due to frictional resistance varies V power n. So where this is 1.72 and 2. So this zone is a fully turbulent zone. Between the points A and C, there lies a transition region. The upper critical Reynold number corresponding to B, so the found for 12,000 to 14,000. The upper critical Reynold number. So, but the upper critical Reynold number is indefinite, being dependent upon initial disturbance affecting the flow shape of entry of pipe, roughness of pipe, etc. Thus, the practical value of upper critical Reynold number may be considered as 2,700 to 4,000. The lower critical Reynold number for flow of fluid pipes corresponding to point A is of a greater engineering importance, as it indicates a condition below which all turbulence entering the flow. So experimentally, the value of lower critical Reynold number has been found to be 2000, and between 2000 to 4000 is transition, and above 4000 is turbulent flow. So the concept of a critical Reynold number, which distinguishes the regimes like laminar, turbulent, is quite useful in study of various fluid flow phenomena. Applying this concept to the flow of any fluid in circular pipes, one may predict that flow will be laminar, otherwise turbulent, etc. based on that Reynold number. It may, however, point out that critical Reynold number is much a function of a boundary of geometry. It's a function of boundary geometry. Thus, for example, in the case of flow between parallel plates, the critical Reynold number computed by using the mean flow velocity and the spacing between the plates is approximately 1000. So, in the case of flow in a wide open channel, the critical Reynold number is approximately 500. And flow around a sphere, the critical Reynold number approximately 1. Thank you. These are the references.
Like, share and subscribe. Hit the bell icon for more updates.